Okay. Recording, yes. Okay, welcome back, folks, to another CSSE 332 section. Today we're going to start our dive into Semaphores, which is our first entry point into concurrency and synchronization between threads. Before we go into that, a few announcements is after today, Monday's assignment should take you like at most an hour. If you understand the stuff today, complete the activity, it should be very, very straightforward for you to do Monday's assignment. The next week is going to be on Monday. We're going to do more synchronization. So that's more of these stuff. And then on Tuesday, we're going to launch milestone 2 for the project. We're going to do that in class. And that will be due 2 Mondays from next Monday, right? So not right after we come back from spring break, a Monday after that, right? So I had to move the schedule a little bit to make sure we cover everything we needed to launch milestone 2, and then we're just going to do that on Tuesday. Makeup exam is on Tuesday as well. I've started grading the exams. Things look good so far, but I still have a whole bunch of your submissions to go through. So we'll see how far I can get between today and tomorrow, and maybe get you your grades as soon as possible. Okay? All right, so where we left things yesterday is we had this for loop, right? It was like int I equals something, I less than max, I plus plus, and you were doing something like counter equals or plus plus inside of it. Right, and we saw that when we used a large number, and we were doing things in parallel using multi-threading, the numbers were not making sense anymore, right? We were expecting 4,000, we were getting 2,000 something, and then we run another time, we get a completely different answer. Okay, so the phenomenon you're seeing here is called a race condition. Okay, but before we formally define what a race condition is, we want to define what a critical section of code is. So a critical section of code is one where one or more threads are accessing a shared variable, and they're making changes to that variable. Okay, so it's a piece of code where one or more threads are accessing and modifying shared variables or shared memory. Okay, so where do you think in our code was the critical section? Yes. Yep, exactly. So in this case, counter plus plus was a critical section. And what we saw happen yesterday was what we refer to as a race condition, which happens when one or more threads enter the critical section around the same time, and try to update a local or a global variable. So the case we had was like pretty much the same case we talked about during the motivation section yesterday, right? We said that the first instructor came and looked at the balance sheet, they saw $1, they added 1 to it, and they wanted to write $2. Before they could write those $2 back, another instructor came in, looked at the books, saw that, you know, there's also $1, they added 1, it's $2, and then both ended up writing $2 in there. So what happened is that we lost in our accounting the $3 that we were hoping to get from the kiosk that we do. Okay, so this race condition in here is the same. What's happening is counter plus plus is basically counter equals counter plus 1. But recall that our CPU or processor does not really understand counter plus 1, right? Counter equals counter plus 1. It understands instructions, byte instructions, or x86 instructions, or ARM instructions. And this turns out to be 3 instructions. There are move, let's use the EAX register, and then I'm just going to write a shorthand here, address of counter. Right, so we're going to move the value of the current value of counter into a register. We're going to add EAX1. So basically, you're just going to add 1 to that register and then store it in the same register. And then we're going to do the opposite, move counter, and then and. Okay, EAX. Okay. So this is basically, I'm not sure if the syntax must not necessarily be correct, but these are 3 instructions: load, add, store. And this is where the problem happens, because a context switch can happen here. Another context switch might happen here. And that's why we're seeing our race condition. So don't be tricked by the fact that you're looking at a single statement. A single statement might be several computing instructions, several assembly instructions, and at any point in time when executing those instructions, a context switch might happen. Yes?
Did you say counter plus plus has a different number of instructions than counter equals counter plus 1? Or you
No, they're both the same. Yeah, so these are equivalent, and they're equivalent to those 3 instructions. Yeah. Yes?
There's a context switch before the add.
Yes.
Won't the scheduler know that there's still, like, because BC wouldn't reach the end, so won't the scheduler like put it back?
Yeah, so it's gonna put it back in here, right? But it's not gonna, it doesn't know that it's gonna load back the instruction, the address, right? Which is why it's creating a problem. There is a way to tell hardware, tell the processor to execute these 3 things in one shot, in a sense achieving what you said. If I read it, put it back, right? But we're gonna get to that probably on Monday. Okay, so this is why we had this issue, and now we want to figure out how we're gonna solve it. So what do you think we should do? Any ideas? What should we be doing to solve this problem out? Yeah.
Actually, a quick question about race. Does the race condition only happen when it actually messes up, or even if it works fine? Like, because when we tested yesterday, it worked fine in some cases, but it's working fine in some cases. Is it still classified a race condition?
Yes, because there's no guarantee that the scheduler is always going to run in the same way you saw it the first time. So sometimes it might not show up until like some edge case where like you're running an important transaction and then things break down.
All right. Thank you.
Yeah. Okay, so what do you think you should do if, let me give you this a little bit of a disgusting example. If you have a restroom that has 1 stall, right? So what do you do to prevent 2 people of like opening the door on each other? If someone is inside and there's someone coming in to try to use the restroom, what do you normally do? Yeah.
You wait for the other person to come out.
Yeah, how do you know that there's someone inside?
The door's locked.
Door's locked. So what we want to do is basically we want to put something like a lock in here to say, when I am incrementing the value of counter, no one else should be incrementing the value of counter, right? And the same thing happens. If I come in and see that the door is locked, I should break the lock and walk in, you're going to have to wait and then acquire the lock once the previous, whoever owns that lock at that certain point in time, opens it up. Oh, so this is exactly what we're going to do today. So we're going to introduce two concepts. The first is atomicity, or an atomic instruction. Okay, so an atomic instruction either executes completely or it doesn't execute. Okay, execute. So what that means is that these types of instructions, they're hit or miss. They either go all in or all out. There's no way to interrupt that type of instruction. Synchronization is enforcing and ordering on the execution. So we're going to use some constructs to enforce a certain order. For example, the order that we said before is at most one person or one thread can be updating the counter at a certain point in time, right? So both of them can't be in that counter plus plus at the same time. The whole block must be protected by that lock that we want to introduce. Okay, and even further, mutual exclusion is when we allow only one thread in the critical section. So it's a special case of synchronization that we only allow exactly one thread or nothing to be in the critical section. So it's kind of like a subset of, yes?
When you say synchronization, is it the same thing as round robin, something like that?
So you can consider round robin as a form of synchronization, but it's much larger than that in the sense that you can use it to even order things as you wish. So you might even go deeper than the round robin and say, I want exactly the tasks to go in a certain way and enforce that. Okay, so let's here introduce our semaphores. So if we want to follow up on the slides, I think we are at this slide. So semaphores, a semaphore is an object with an integer value. Okay, it's simply an object with a certain integer value. So the properties are that the changes to the integer value happen atomically. So we're going to talk Monday about how we achieve that part of a semaphore. But if I want to change a value in a semaphore, it happens atomically, right? And the way it achieves that is it uses hardware support to achieve atomism. So does anyone know what the actual meaning of the word semaphore is? Have you ever encountered it before? So in aviation or in navigation in the sea, there's usually those people you see with the flags. Those flags are called semaphores. And in sea navigation specifically, each flag has a certain meaning. So if you want to tell an incoming boat something, you just raise a certain type of flag. If you want them to wait, you raise another type. And the semaphores in OS are called because they are used as a way to tell the threads that if someone is in the critical section, they're going to wait. If that someone is out of the critical section, they can now go in. Okay, so we're going to see that in a few. Now, a semaphore has an integer value, and we're going to call this integer value x. And we're going to first introduce two operations that you're going to work with a lot over the next week. The first one is Semaphore Weight, and the other one is Semaphore Post. Okay? So Semaphore Weight does the following. One, decrement x. So we decrement the value of x in the semaphore. The second thing we do, check if x is less than 0. So we're going to do an if statement or a while statement if x is less than 0. If it's true, then go to sleep. Okay? And you sleep not for a specific amount of time, but until someone else wakes you up. Okay? Second thing, if it's false, so this means x is greater than or equal to 0, we're gonna go into critical section. Okay? So we're gonna see how those play with the post after we just introduce post. So what post does is pretty much the exact opposite. First thing it's going to do is going to increment x. Second thing it's going to do is that it's going to wake up a waiting or a sleeping thread. So it's going to go in and check, is there anyone sleeping or waiting for the critical region to be open? If so, it's going to wake them up and they're going to go into the critical region. So if there are more than one thread waiting, then we're going to need a third thing, which is a queue for waiting threads. And then we're just going to modify this, wake up the sleeping thread at top of queue. So if there are two, I wake up the one that first came in. If there are three, we get the first one, then the second one, then the third one, in that order. Questions? Okay, so how do you think we can use these two things to protect our counter plus plus? So we had counter plus plus. So how can we use these post and wait constructs to protect our counter? Yes?
Wait right before and then after you're done with it, post.
Yes, exactly. So what we're going to do is we're going to sem wait, and we'll see what parameters we pass to it later, and then sem post after. So what happens here? When we call sem wait, either someone is already in the section, in the critical section, so we're going to wait and sleep until they're done, or there's no one in the critical section, so we can go into the critical section. Now, once we're done from the critical section, we're going to tell everyone else that it's safe for you to go into the critical section, which is we're going to achieve using the post. Okay? So wait before you go in, post before you go out. So going back to our analogy, you knock on the door. If there's anyone inside, they're going to tell you there's someone inside. The door is locked. Once they leave, you go to sleep after that. Once they leave after finishing up their business, they're going to wake you up, and now you can go into the critical. Okay? So pretty much that's exactly what we're doing. Now, what we looked at exactly here is called the binary semaphore, or a mutex coming from mutual exclusion. So a binary semaphore means that exactly one thread can be in the critical section at any moment in time. There can be either 0 threads in that section, so no one wants to go in, or exactly one thread in that section. But sometimes you might need more than that. So if you need more than one process to enter the critical section, we use what we call a counting semaphore. So this means more than one in critical section. Okay? Questions? All right. So what is left for us to do is to figure out how we're going to initialize and create these semaphores. So the way we do that is we use the syntax sem_t, and that's the type of a semaphore, and you define it, let's call it s. And the way you initialize a semaphore is you call a function called sem init. First parameter is always the address of your semaphore, so a pointer to the semaphore you want to create. Second thing you want to do is pass 0 in here, and third is the initial value of x. So this 0, this class, you're going to leave it as a 0 always. What it means is that share the semaphore between threads of the same process. And x is initial value. So the second parameter, you can actually share a semaphore between processes, but we're not going to do that in this class. We're going to focus on just multi-threading within the same process, so we're always going to plug in 0 in there. X is the initial value that you want to give to your semaphore. So if I want this to work, what should be the initial value of my semaphore? And this is the definition of wait and post. What do you think it should be? Yes, 1, right? So if for a binary semaphore, initial value is 1. Okay, so that the first time someone wants to come in, they're going to decrement 1. The value is going to be 0. They're going to do the second step, which is check if x less than 0. It's not going to be less than 0, so they go in. Next one comes in, they're going to decrement x. It's now -1, so they're going to sleep, right? So that's the reasoning here. Figuring out the initial value of a semaphore is sometimes what can make or break your code, right? If it's a binary semaphore, we always know it's 1. But if you're using it as a counting semaphore, sometimes very bad things can happen if you're not careful about the initial. Yeah.
Usually, like there are times when, like, you want like you don't always know the number of threads that are running at that point.
Yeah.
How do you choose the initial one?
So you have to know something about your.
You know, like a maximum, right?
You can set it to a maximum, but you have to make sure if you set it to a maximum, then if you set it like, let's say, to 100, then there can be 100 threads in there at the same time. right? Also, the initial value is not a maximum.
Yeah.
So you can write a loop that runs post, 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 and keep doing that. It's useless, but you can do it, right? So whatever you set as initial value is not a maximum that you're going to guarantee that the value of the semaphore is not going to grow above, right? So be careful about that when thinking about it. So a helpful hint I find when thinking about initial values is if x is positive, what does that mean? How can we interpret x being greater than 0? Yeah.
There's either there's at least one more thread that.
There's at least one more thread that can go into. Can go into the critical section. In fact, it turns out it's even more accurate than that. X is exactly the number of threads. So at least one, but X is exactly the number of those that can go into critical section. And it's going to be greater than or equal to 0. If X is less than 0, how can we interpret X at that? Yes? Yeah, exactly. So there are number of threads waiting for the critical section. So that's why when we were thinking about the initial value of our binary semaphore, okay, we need to allow at most 1 or exactly 1 or 0 threads to be in the critical section, so the initial value should be 1. If we put it to 2, then 2 of them can go inside, which is not what we want, right? So that's why we start from 1. Questions? Okay, so this puts us here, which is application A. I think we're good on time. So the rest of this lecture is basically we're going to walk through, or I'm going to walk you through the first one of our activities, and then there's 3 other activities that you're going to do for tomorrow. They're all direct applications of semaphores. We're going to use them for different things. If you keep going through the slides, you're probably going to see the solution. And I also gave you the solution. So there's more explanation in the slides if you're not. If you're struggling a little bit, and you can always reach out to me and ask about the in-class activity. So let's go ahead and start our activity. I think I updated everything. Yep. So it's going to be under activities and semaphores, 18 semaphores. So the first one we're going to do is activity A. And can you look at this piece of code and tell me what you think is happening in each thread?
Summing how many, or it's summing the total values in the array.
Yeah, exactly. So what this piece of code is doing, it's that each thread has its own starting index and its own share of the array. And what it's doing is that it's summing up the items in that share. It's accessing a global variable called sum, which is defined here as an unsigned long one. So we just want to allow 64 bits of size of the integer. Okay? So what exactly is happening is the following. We have one big array. We're going to split it in half. So if this is n elements, this is n over 2, n over 2. Then T1 is going to add up all the elements in the first half, and so on. T2 is going to add all the elements in the second half. And eventually, we should see the actual sum coming up. So, can you tell me where there could be a critical section and a race condition in this code? Yeah, so in here it's pretty much the same thing. Instead of incrementing counter +1, we're now just adding sum a of I to the actual sum we have. Sum is shared between the two threads, so we have a race condition in there, and it's a critical region. So if we want to confirm that, let's go ahead and compile, and then we're running a.bin. So initially the sum is, so just so you know, the value is initialized to have all ones. So when you sum everything up, you just get the size of the array. So if we run it with 1024, we always get the right result, right? But let's try to increase it, and we're going to start seeing things go bad. So this is 100,000, or yeah, 100,000. We're seeing 97 something. Run it again. I see 84. So we know that we have a race condition. And this is one example where if it runs once, it doesn't mean that that there's no race conditions, right? It might be just didn't hit the exact setup that leads to a race condition. So let's go in and solve this part and see how we're going to implement this activity. What we want to do is that we want to protect our critical region. So what do you think we should do, and how do you think we should do it? So first question, do we need a binary semaphore or a counting semaphore? And then where do we place weight and post? Yeah.
I think we'd use a binary one because, like, you risk, like, whenever you have more than one in there, you start making risks. So I'm assuming the risk goes up the more you have, but your risk starts as soon as you have.
Yeah. So you need a binary semaphore because basically I want to allow at most one thread to be running sum equal plus equal array. So where do I place my weight and my post? Yeah. Yeah, exactly. So let's go ahead and implement this. So we're going to protect this statement with our binary sum. So we define our semaphore as, as a global variable, and I'm going to call it mutex just so we know that this is a binary sum. First thing we want to do is we're going to initialize the semaphore. So we do sem init, and we pass the address of it, 0, and our initial value for a binary semaphore is always going to be 1. Okay? So next is we're just going to do some weight here on mutex, and then some post on the mutex. Okay? That's it. That's how we protect this code. Last thing we want to do is just to make sure that we include semaphore.each. Okay? So let's compile again, and then run it with 100,000, and there we go. We don't have that problem anymore. No matter how many times I run this, I always get the correct answer. Okay? So, a question, is this the best that we could do? Can we do any better than this? Think about doing things in parallel. Can you do things in a more separate and individual way than what we're doing now? Yeah. Say that again. So if we divide it even further, but effectively, eventually, they're still going to each thread is going to do n over 2, right? So we can either increase the number of threads, but let's say we don't have the ability to increase the number of threads. Any other thoughts?
You're just telling me their own counters and so on.
Yeah. So if you notice that summing these values and summing these values are independent, right? I don't have to know the sum of the first half to know the sum of the second half. The sum of the array is the sum of its is basically the sum of its two halves. So why do we want to keep doing, you know, I wait for a mutex here and then I write. I wait for a mutex here, and then I write. And I wait for a mutex and then I write. We're just doing this alternation that's not helping us very much, right? So what we're going to do is that we're going to have a local sum in here and a local sum in here. And then finally, we're just going to do sum plus equal to local sum. And the only place where we have to protect or guard is just this part. So some weight, some cost. Okay? So that's even better because accessing, if you recall what a semaphore is, it has to ask the hardware to provide support for atomic instructions. Those instructions are not free. And if we want to do a lot of these instructions, then we might end up paying too much overhead for our parallels. All right, so we need to be careful. If we can minimize the critical region that we have, then it's always better to do that. So I'm not going to implement this in here, but I'm just going to show you the outcome of this. In the solutions, I added some timing information to show you how does this fare compared to running just the sum in one single shot. Okay, so if you run the solution, you're going to get timing information. All right, so here's what happens now. We're looking at 1024 elements. We're doing this sequentially, and we're doing this using our optimized solution. And you're going to see that sequentially, it's actually pretty much faster, right? And that is because 1024 is really very small to pay any penalty in context switching or in mutual exclusion. All right, so 1024 is not enough for us to account for the overhead of context switching and of doing synchronization. But as soon as we start this starts going over, let's say 100,000. I think we need a little bit more. There we go. So as soon as we hit 1 million elements in that array, you can see that it's 2 milliseconds sequentially, 1 millisecond in parallel. You can increase one further as long as my tablet supports that. And yeah, so it's 15 milliseconds compared to 9. So you can always see it's about half, right? It's not always exactly half, but we're about cutting the computation time in half when we're doing. All right, so I just advise you to play around with this a little bit. You can actually, let's see if we can do that here. A solution. Let's see. Let's compare this to the case when we do this. Okay. So let's compare it to our initial case. Let's see if this is better or worse. So let's go back and run 1 million, and you can see how bad it is. It's, I think, 100 times as bad as or worse than the sequential one, because there's a very, very, very high penalty we're paying for synchronization. If we go up even higher, I think we did 5, then it's 11 milliseconds compared to half a second, right? It's really bad. So although we're trying to do things in parallel, we're paying too much penalty in the all right. So that's all I had for today. I'd like you to use the remaining 9 minutes-ish, 10 minutes to keep working on the activity. You have 3 more parts. The last one is the most difficult to understand, but once you do that, the assignment on Monday becomes very easy. Okay, so if you have questions, just let me know and I'll walk around and see what you guys have.
Are the instructions included in?
Yeah, except for the first one, which we just talked about. For B, C, and D, it's on the slides and in the fine.
For A, you wanted a specific way, like if we updated it, do you have to complete it as we did in class?
Yeah, so for activity A, you just have to do the final thing we talked about.
Oh, I was wrong. Yeah.